Mr. Sarles here once again, lesson 5.3, day number 1. We're going to talk about standardized scores, z-scores today. To introduce this topic, who bowled better, Taylor or Mr. Sarles? Taylor had an average of 190 and a standard deviation of 15. Mr. Sarles averaged 200, standard deviation of 40. To see who bowled better, we actually bowled one game each. Taylor bowled a 220, I bowled a 250. So who bowled better? Pause, think about it for a second, come back. Now if you're just looking at the raw score, I got a higher score. Higher's better in bowling, so you could argue Mr. Sarles did better. But kids after looking at it a while would make this argument. They'd take Taylor's score, subtract her average, and divide by 15, and they got an answer of 2. Did the same for me, and I only got a 1.25. The question is, what do those two numbers represent? So looking at Taylor's 220, that is 30 above her mean, which is actually 2 standard deviations. So what does the 2 represent? Taylor bowled 2 standard deviations above her mean, whereas I only bowled 1.25 standard deviations above my mean. This number of standard deviations concept is called a standardized value. Write this down in your notes, z-score. The value you're looking at minus the mean divided by the standard deviation. What does it tell you? It tells you how many standard deviations the observed value is above or below the mean. Pictured on this page is a standardized grading curve. At Gustavus, a couple of my entry-level classes my freshman year used this to determine the grades in the class. The mean, and then these were the standard deviations away from the mean. So if you got 1 standard deviation above or below the mean, anywhere in there you obtained a C. Between 1 and 2 standard deviations above the mean, you'd earn a B, etc. Okay, on this page I have 2 students, Grace in AP Stats and Brady in English. Here are the scores they got on their test, and here are the mean scores for the class and the standard deviation. What I want you to do is determine a z-score for each of these students, and then determine what grade they would get in the class based on those z-scores. Pause the video, come back in just a moment. Okay, using the formula up here, Grace would get a z-score of 2.25, meaning she scored 2.25 standard deviations above her class's average. 2.25, she would actually receive an A on that test. Brady, you get 1.6 for the standardized score, meaning Brady scored 1.6 standard deviations above the mean of the English class. 1.6 would be right about here, so Brady would have earned a B. So notice, standardized score tells me a lot more than the raw scores. If I had asked you at the beginning, who did better, Brady or Grace? Brady got a 91, Grace got an 88. You might have thought that Brady did better. Relative to their classes, gives you more information. Okay, for this next problem, ACT math scores, normally distributed with a mean of 21, standard deviation of 3. Calculate and interpret the z-score for each student. Pause the video, try doing part A, come back when you're ready. Okay, take Dylan's score minus 21 divided by 3. You get 2. What does that mean? A positive 2 tells you Dylan's ACT math score was 2 standard deviations above the mean ACT math score. Do the same for B. Greg's ACT math score. 13 minus 21 divided by 3, you get negative 2.67. So what does the negative mean in this case? Greg actually scored 2.67 standard deviations below the ACT mean math score. All right, do stands. Stan got a score of 21, which is exactly on the mean. So you get a z-score of 0. So a z-score of 0 tells you Stan's ACT math score is exactly the same as the mean ACT math score. Okay, this time I give you the z-score and want you to work backwards. So David got a z-score of 3. What was his raw score? So I'm going to take 3, plug it into the formula over here for z. X I don't know, the mean is 21, the standard deviation is 3. So plugging it in looks like that. Cross multiply, 3 times 3, I get my 9, and then add 21 to both sides. So David got a score of 30. Do the same with Pat and Jordan. Come back when you're ready. For Pat's score, I believe I turned negative 1.6 repeating into an improper fraction, which is 5 over 3. Made my math a little easier to do. Negative 5 over 3, x minus 21 over 3. Multiply both sides by 3. The denominators cancel out. You get negative 5 equals x minus 21. Add 21 to both sides. Pat got a score of 16. Which makes sense. It was below the mean, which you should double check to make sure that the negative matches the concept. Okay, Jordan's z-score 0. I'm not going to do any calculation. Jordan scored a 21, which is the same as the mean. Okay, pause the video for a second, read through this problem, and then we'll come back together in a moment. Okay, the big question here, Eleanor took both the SAT and the ACT. Her college will only accept a submission from one of the two schools, not both. Which score should she submit? Explain your reasoning. I'm going to find a z-score for both tests. For the SAT, she got a z-score of 1.8. For the ACT, she got a z-score of 1.5. Okay, in terms of this problem, having a higher z-score is better. So, Eleanor scored 1.8 standard deviations above the SAT mean score, but only 1.5 standard deviations above the ACT mean score. Thus, she should submit her SAT math score. Exactly the same problem. To confirm your answer, this time I want you to find her percentile ranks for both tests. I've drawn the distributions for you. Pause, see if you can think how you'd figure this out. Come back when you're ready. Okay, I'm going to start with the ACT. She scored a 27. And percentile rank means the percent you beat. So I'm going to mark that down as a 27, area shaded to the left. SAT, she scored a 680. That would be that shaded region. In both cases, I'm given scores and want to find a percent. That is a normal cumulative density function calculation. On the left-hand side, for the ACT, negative infinity, large number on my calculator, up to 27, mean standard deviation. I get 0.9332. For the SAT, negative infinity up to 680 with a mean of 500 and a standard deviation of 100. There I get 0.9641. So Eleanor scored higher than 93% of those kids taking the ACT test and 96% of those taking the SAT math test. This confirms again that she should submit the SAT score. Okay, one more problem. This time it says instead of using the original data, use z-scores to find the percentiles. Remember for the ACT a couple slides ago we got a z-score of 1.5, and for the SAT we got a z-score of 1.8. Let's look at the scaling on the bottom here. Instead of 18 for a z-score, if I put 18 into this formula, well, the mean was 18. 18 minus 18 divided by 6. That's 0 divided by 6. I would get a z-score of 0. Let's put in 24. 24 minus 18 divided by 6. That ends up being 6 divided by 6. I get 1. Put in 30. 30 minus 18 is 12 divided by 6. I get 2. Continuing on in this manner, look what happens if I take the raw data and actually standardize it. I will get that same numbering that you saw on the standardized grading curve that I talked about earlier. What happens if we do the same thing on the SAT? Well, the mean was 500. 500 minus 500 divided by 100 this time. Again, I will get 0. 600 minus 500. Notice I'm going to get this same patterning I got before. So, in both cases, if I look at the standardized scores, I will get 0 for my mean, and my standard deviations will count by 1. And on here, I had a z-score of 1.5. Here, I had a z-score of 1.8. Okay, doing my normal cumulative density function calculations now. Notice here, I changed x to z because we're on a z distribution. Here, negative infinity up to 1.5 this time. The mean is 0. The standard deviation of this graph is 1. Here, negative infinity up to 1.8. The mean is again 0. Standard deviation is 1. Notice my percents are exactly the same as I got on the last slide. So, some takeaways. If you use the standard normal distribution, the mean will always be 0, and the standard deviation will always be 1. That concludes today's lesson. See you guys tomorrow.